Potential energy formulas. The symbol for potential energy, of course, is a capital U. Which I think goes with the drum. I think your text wants to use capital PE. Let's just do it right. All right. For each conservative force, there exists a potential energy formula. Or shorthand notation.
Is that a line or an upside down A?
That's upside down A.
Oh,
It means for each and every. And then the backwards capital E means there exists. So we have gravitational force and weight as our conservative forces. There's potential energy formula that goes for each. So the little chart here, conservative force, potential energy formula. If we're dealing with weight in G, the formula is mgh plus a constant. If we are dealing with a generalized gravitational force, which we'll get to in chapter 9 or 10, I think it's 10. Big G, mass 1, mass 2 over r squared. The formula, negative big G, mass 1, mass 2 over r, plus a constant. All right, so those are the two that we'll get to in the first 10 chapters. Later on, we will get to ideal elastic. So, ideal elastic. So we have lowercase k, delta x, negative 1/2 k delta x squared. And we'll get into that later, what that stuff means. If we get far enough, there's also the electric force, which we'll deal with when we get there. Yes?
What is underneath the G and one X2 over, what is that underneath?
But here,
Yeah, like,
this is negative big G, mass 1, mass 2 over r plus a constant.
so FC is conservational force.
Conservative force.
Conservative force, sorry, not conservation. Conservative force, and then U is potential energy.
Yes.
So those are those equations that are,
So if I have weight, if I'm doing a force diagram and I have a weight involved, then this gravitational potential energy would be involved if I do look at it from a gravitational point.
okay,
If I'm dealing with, say, outer space, that's the potential energy formula.
for energies.
If I put an ideal spring or something like that into it, that's going to show up.
Okay.
We're going to do an example in a bit. Other questions? Right, why don't we take a break, come back, and continue rejoicing. Yes?
And I just made it home too, so.
Okay, so let's start with a mass that is falling. Why do objects fall?
Can you repeat?
Why do objects fall?
Gravity?
Okay. The gravitational force, is it conservative or non-conservative?
Conservative.
Therefore, the total energy is conserved. So if I have this object and I say it has a potential energy of 500 joules, joules being the SI unit for it, and no kinetic energy, what's my total energy to start with?
500.
Yeah. So my total. Since gravitational force is conservative, the total should stay the same. So when the potential energy is 400 joules, what's the kinetic energy? Say it again?
400?
Yes. Units?
J.
Oh, wait. You said 400? That's not right.
Zero?
Somebody say 0?
100?
Yeah, 100. Because the total. Total stays the same.
400.
Oh.
It's staying.
When I have 300 joules of potential energy, how much kinetic would I have?
200.
And when the potential energy is negative 100, what's the kinetic?
600.
Negative potential energy is possible. Negative kinetic energy, not so much. Because the speed is squared. So, and mass is a positive number.
What would be an example of a negative potential energy?
Besides that,
Yeah, like with like a real world like object.
all right, let's do it. I have an object, we'll make it a 5 kilogram mass. And I'll put the ground down here. And it starts out let's just say 40 meters above the ground. Starts at rest. Initial speed is 0. So what I want to do is figure out the total energy here, and then I know the total energy the entire time. Well, let's force diagram. What are all the forces acting on it?
Gravity.
The force.
Oh.
Normal force.
Someone just said something else?
I said normal force.
And was it touching?
Nothing, yeah.
The normal force?
Or weight.
Yeah, weight. Force due to gravity, gravitational force, or weight. Gravity, huge topic, of which we're studying small parts of it. All right, so I have weight acting down. Conservative or non-conservative?
Not conservative.
It is considered.
Oh, it is.
It is conservative. All right, so energy is conserved, so I want to figure out what's my total energy to start with, and I know what it is until it hits the ground. So my total energy, kinetic plus potential. Take a small little pause right here. I mentioned a third energy, rest energy, but I'm not bringing that into it. If I'm just looking at potential and kinetic, not looking at the rest energy, then this is known as the mechanical energy. And Hewitt talks about the mechanical energy, and that sometimes throws students about what mechanical energy is. Mechanical energy is, we're not talking about rest energy. We would only bring rest energy into it if the object burst into flames on the way down. So, not something most people deal with in their everyday life. All right, so weight is a conservative force, therefore has a formula for potential energy. So we'll have the kinetic energy plus the gravitational potential energy. Now we do have two types of gravitational potential energy. This is the one where G is relatively constant. And that's a capital K. I'm about to ask that question again. What's the formula for kinetic energy? Not quite as nice as the last time. We'll get there. And the formula for potential energy? All right, so the proper response to what's the formula for potential energy, if I just ask it like that, is which one?
mg plus c.
The one, so what's the formula for potential energy?
Which one?
Thank you. The one associated with weight. And now we bring in the other bit. What's the formula for the potential energy, gravitational potential energy, if we're talking about weight?
mg
That's the force.
h plus c. mgh plus c.
Yeah, mgh plus c. So that sum should be the same no matter where I am in the problem. So if I want to know my initial kinetic energy, my initial energy, well, I just need the initial speed, initial height. What is my initial speed?
0.
Yep, give it. Right there.
No.
So this is 0. Plus m, which is 5 kilograms, times g, which is 9.8 meters per second squared. And what is the initial height?
40 meters.
Anyone want to disagree with that? Okay. Monica just made an assumption. What did she assume?
The object is the same at that height, at the 40.
Sorry, what did she assume?
That the object is at the height of 40 meters
Above what?
above the ground.
No, that was given in the problem. That's not the assumption she made. All right, we'll keep going. Plus some constant. All right, so if now we multiply all that out, we get 5 times 9.8 times 40, which is,
1960.
say it again,
1960.
1960
Yep.
units?
Meters.
Cancels it. Kilograms per second squared.
Say it one more time.
Kilograms per second squared.
You left something off.
Kilograms times meters.
Is there
Second squared.
I lost, after meters, what'd you say?
Over seconds squared.
So you did kilogram meters over second squared?
Yeah.
That's a newton. That's the unit of force.
Do the
Like-
meters not cancel out?
No,
No.
Meter squared.
yeah. So kilogram, meter squared per second squared, which is just a joule. So 1960 joules. So as it falls, what's going to be the total energy? Yeah, joules.
Joules.
Yeah, until a non-conservative force is involved, that's my total, that's the entire time.
We didn't do anything with C though.
You're right. Oh, that's right.
Plus C, plus.
Okay, so you don't have to solve for C.
Well, usually not.
Okay.
All right, so if I want to know how fast it's going when it is 20 meters above the ground, so it's going to fall, I want to figure out how fast it's going at this point when it is 20 meters. Well, I just basically go through the same thing. We'll come back to this. So when it's 20 meters above the ground, I know my total is going to be 1960 plus some constant. It's equal to 1/2 times, so 1/2 mv squared final plus mgh final plus a constant. I'm trying to figure out my final speed there. Plus 5 times 9.8 times, what's my final height?
20 meters.
Plus C. And the reason why we don't need to figure out C is C cancels out. I have it plus C on both sides. Because the actual value of potential energy is not as important as how the change.
Okay.
Working out the fancy math, I got 1960 is equal to 2.5 v squared plus that, which should be 980. Subtract that from both sides, and I get 980 is 2.5 v squared. Divide by 2.5. And 980 divided by 2.5.
392.
392. And so my final speed is
392. 392.
no, that's speed squared.
Oh.
Square root of 392.
19.8.
10 units. Not for speed.
Meters just then.
Yeah. So if it falls 20 meters, starts at rest, it falls 20 meters, and it's going 19.8 meters per second. Questions up to here? All right, still don't want to forget Irvin's question. The assumption, right here we have height. Height's there, height's there. The initial height, Monica said 40 meters. Height is the distance above something. And so if the initial height was 40 meters, it was 40 meters above what? So the assumption that she made was that the ground was 0. That this is where height is equal to 0. Suppose we had said that the height was 0 here. What changes? Well, that changes. If I say this is 0, then it starts out 20 meters. Then this starts out at 20. This is 980. And then over here, what's the final height then? If we say height is equal to 0 at this point,
20.
yeah. Oh wait, no, sorry, say it again.
20.
Nope. When it's fallen 20 meters,
Oh, 0.
0.
0. So that becomes, go forward, over here. That becomes 0. And what we're left with is just that. So where height is equal to 0 is arbitrary. You get to decide where 0 is. That's the power of the plus constant, is it gives you the flexibility to decide where you want 0 to be. So if I made this height is equal to 0, and then I asked how fast is it going just before it touches the ground, well, my initial energy stays the same. Again, height is 0 here. Get rid of that. On the ground, what is the height?
40. Wait,
So 0 is here. It starts out here, 40 meters above the ground. I'm saying h is equal to 0 here. What would this height be?
negative 10.
Negative 20. Negative 20. Sounded like you were saying 40. 20, okay. Now, in the first couple chapters, we could decide what's positive or negative direction. I will tell you, when you're dealing with potential gravitational potential energy, MGH, that's the positive height, negative height. So negative 20, which makes it negative 980 and 980. So the question that Irvin asked earlier was, what would negative potential energy mean? It just means that we've chosen 0 to be someplace in the past. And so is it practical to do that? Sometimes. If I ask a two-part question where h is equal to 0 here, how fast it's going after it falls 20 meters, setting h is equal to 0 here is convenient. How fast is it going just before it touches the ground? I could reestablish h is equal to 0. I'd have to recalculate the initial energy, and I can still solve it. Or I could keep h is equal to 0 here, don't have to resolve initial energy, just have a negative height down here.